Good morning, students, and welcome to today's session. So, last time we learned about the basics of frictional force, and we understood about the two types of coefficients of friction: coefficient of static friction and coefficient of kinetic friction. So, we'll be continuing from that point onwards today. So, let's take a quick recap of the concepts of friction that we started with in the previous lecture last week. So, this is friction session number 2 for us. So first of all, we saw that friction is a contact force that acts tangentially at the surface of contact. Oppose slipping. Then we saw that depending on whether the surfaces are actually slipping or they are at rest with respect to each other. Two types of friction, static and kinetic friction. So this is the friction that acts between two surfaces to prevent slipping. When there is a tendency to slip. Whereas kinetic friction is the type of friction that acts when there is actually slipping. And it acts such that it opposes the slipping. Right, so these are the two types of friction. Now we saw that static friction can in general have any value from 0 up to a maximum limit depending on the amount of external force that is trying to create slipping. So this μs is called the coefficient of static friction. And obviously n is the normal reaction. Whereas the kinetic friction, irrespective of the external force, is always equal to mu k into n, where this is the coefficient of kinetic friction. And in general, we saw that coefficient of kinetic friction is less than or at best equal to the coefficient of static friction. Okay, so these are some of the aspects that we learned last time. So now let's proceed with an example to take this further. So in our next example, what we have is a rough surface like this, which has coefficient of static friction given to us as 0.25 and coefficient of kinetic friction given to us as 0.24. Okay. Now on this, we have a combination of two blocks placed like this, such that this surface is smooth. So there is no friction. Coefficient of friction is 0. And the blocks are initially at rest. So the mass of the block A is given to us as 20 kilograms. The mass of the block B is given to us as 4 kilograms. G is 10 meters per second square. Now a horizontal external force is applied on the block A. So find the accelerations and the friction on the block A if F is equal to 50 newtons. F is equal to 100 newtons. So let us see this equation. So suppose we are pushing this block B with a horizontal external force F now, whereas initially the system is at rest. Yes, Prince, you have to work out this example now. In fact, do one thing, increase this to 55 newtons. It's applied on B. Yeah, the force is applied on B, as shown in the diagram. It's applied on the lower block. Yes, people, I'm waiting for the answers. Okay, it's pretty simple really. If you had just revise the concept of friction from the previous couple of lectures, I told you to prepare from reference books also. Start working a little bit harder. Anyway, so let's understand. So when you look at the block A, the weight of the block is equal to how much? It's equal to 5 kgs mass, so it's 50 newtons. Sorry, 4 kgs mass, so it's 40 newtons. So there's a normal reaction acting on it, which is also equal to 40 newtons. So now when you look at the block B, you can see that A is applying a downward normal reaction of 40 newtons on it. B's own weight is equal to 200 newtons because mass of B is 20 kg. So the normal reaction the ground applies on B is equal to 240 newtons. You can see that NB will be equal to Na plus weight of B. So you can see that normal reaction will be this much. So when we apply an external force like this on B, now the friction, so maximum static friction possible, that is going to be what? The coefficient of static friction into the normal reaction between B and the ground, because the contact is between B and the ground. So this is going to be 0.25 into 240. So that is 60 newtons. So maximum friction available is up to 60 newtons. So from this we can see that unless F is greater than 60 newtons, the block B will not move. That is, acceleration will be zero, and the friction will balance F for F less than equal to 60 newtons. Whereas if F is greater than 60 newtons, B will slip, and a kinetic friction, that is 0.24 into 240. So we'll work that out, but that is the acceleration will be non-zero. So now work out the individual parts. Yes, Tantresh, very good. This is correct. Oh, we just have to interchange the masses. You can see that B is the heavier block in the diagram. But actually, it will not make a difference. Even if the masses were in reverse order, the normal reaction at the ground would be the combined weight. So the answer would have been the same. Okay, you understanding, Prince? B is the heavier block, but the thing is, even if the masses were interchanged, the normal reaction at the ground would have been the same. Okay, so the answer for part A would be the same. Okay, so now let's work out the individual parts. So you can see here that in the first part, if the force we are applying is 55 newtons, you can see it is not enough to make the block be slip. So what will happen is that the acceleration of B will be zero. Obviously, acceleration of A is always zero. Okay, and the static friction is equal to F, equal to 55 newtons. So this becomes the answer for the A part. But B part, when we increase the force to 100 newtons, now B slips. So what will happen is B will slip from under A. Eventually A will fall off, but we are just worried about the initial instant. So when we start applying this force, there'll be kinetic friction acting like this, but there won't be any horizontal force on E. So acceleration of A will be zero at that moment. Acceleration of B will be non-zero. So acceleration of B will be F minus kinetic friction divided by mass of B. So this will be 100 minus mu K into normal reaction at B divided by 20 kg. So this we saw is 57.6. The acceleration of B will become 100 minus 57.6 will give us 42.4, right, divided by 20. So that is 2.12. So 2.12 meters per second square will be the initial acceleration of B. So what will actually happen is that eventually A will slip off B, but we are only worried about the initial instant. So when we start pushing, this will start moving. Eventually, after some time, this will happen. Then this will roll over. And when, okay, but we are not worried about all this. We are only worried about initially what is happening. So that is this. Okay, so hope both the parts are clear. First part is very simple. Okay, because the force you are applying is less than 60 newtons. Now we saw the maximum friction. Yes, that's correct, Anmol. So A stays stationary with respect to the ground till it rolls over or slips over like this. So B is slipping from under A. Okay, so how we know this is happening? We know that because in the previous section, we have calculated the maximum friction. Let's go back to that, this thing. We've calculated the maximum static friction which is available, this one. So we can see that unless the force is greater than 60 Newton, the block B will not move. And if the force is greater than 60 Newton, then kinetic friction of this much will act on it. So we just apply this condition now on the given data, on the given values. Okay, next let's see another simple question based on the same concept. Okay, Prince, you haven't finished writing. Okay, finish this quickly. Okay, done, Prince. Okay. Yeah, so let's proceed to our next question. So now we have this situation. This is a rough surface which has coefficient of static friction 0.4 and coefficient of kinetic friction 0.3. We have a pulley like this attached at the corner and a light thread going around the pulley. Connecting a combination of two blocks. So given mass of the block A is 10 kilograms, G is 10 meters per second square. Find the acceleration of A and B if mass of B is 20 kg, mass of B is 60 kg. And C part, find the minimum mass of B in order to, or let's say find the maximum mass of B such that the system does not move. Okay, work this out quickly, people. Hence, the question is pretty straightforward. The mass of B is given as 20 kg in this situation in part A, whereas the mass of block A is 10 kg. Okay. So obviously you can see that it cannot be greater than G. How can the acceleration of the system be greater than G? Okay. Anyway, so let's understand this. Okay, let's look at the forces. Now, weight of E is 100 newtons. So normal reaction acting on A here is 100 newtons. So as far as friction is concerned, we can see that maximum static friction is going to be how much? 40 newtons. Whereas kinetic friction is going to be 30 newtons. Okay. So now you can see that the condition for equilibrium so for equilibrium of the system, that is acceleration being 0, tension should balance the weight of G, and for on E, tension should balance with static friction. So that means static friction should be equal to the weight of B. So that means the weight of B cannot exceed this limiting value, this value. So for equilibrium, okay, so that means mass of B should be less than equal to 4 kg for equilibrium. So therefore, if MB is greater than 4 kg, then the system will accelerate. So we will have this situation only, but with acceleration. So that is why in both the individual parts I've given you, there will be acceleration. Okay. So therefore, the system will accelerate. And this friction will be kinetic friction. So for B, we'll have the equation weight minus tension is equal to mass into acceleration. For A, we'll have the equation tension minus kinetic friction is mass into acceleration. Now add the two equations. So weight of B minus kinetic friction is sum of masses into acceleration. So acceleration becomes this minus mu k into normal reaction. Now just substitute the values. So mass of B we have taken as 20 kg. Coefficient of kinetic friction is 0.3. Mass of A was 10 kg. Okay. So 17 by 30 times G. Okay, similarly, you have to work out the second part. Yes, that's correct, Ganesh. Correct, Antesh. Okay, so it's a pretty simple case of substitution of the values. So for the second part, you just replace the mass of B, 60 kg. So you'll finally get this acceleration as 60 minus 3 upon 70 G, or 57 by 70 G. So taking G as 10, you will get it nearly something like this. the moment it starts slipping, now let us see what is happening. The weight of block B, Anmol, in both the cases we have taken, part A and part B, 20 kg or 60 kg, whichever. The weight of block B is so much that it starts pulling the block in, because it overcomes friction. So the moment slipping starts, what type of friction will act? Kinetic friction. No? Static friction only acts in that situation where it can balance the tension to keep the system at rest. That would only happen if the mass of block B was less than equal to 4 kg. You understanding? Okay. So the moment the mass of block B is more than 4 kg, we know slipping will start. So the acceleration of the system will be such that the amount of friction taken into account will be kinetic friction. Okay, now next let's move on to the very important part of friction on an inclined plane. Okay. Right. Right. So next let's move on to friction on an inclined plane. So we have a situation where we have an inclined plane which is at an angle theta with respect to the horizontal, and it has a coefficient of static friction mu s and a coefficient of kinetic friction mu k, and we've kept an object on this. So on resolving the forces, we can see that the components of weight, as we know, are mg sine theta and mg cos theta, because we know that this angle here is theta. So the normal reaction, again, we know is equal to mg cos theta. So the normal reaction becomes mg cos theta in magnitude. So that tells us the condition on friction that is available. So the friction will either be able to prevent slipping altogether or it will oppose slipping, whatever be the case. So here, the limiting friction available, that is static friction's maximum, is mu s into normal reaction. So that is nothing but coefficient of static friction into mg cos theta. Okay, so therefore, the condition for no slipping, that is for the block to remain stationary, for static friction be able to prevent slipping. The condition for that to happen is that mg sine theta should be less than or equal to maximum friction available. So mg sine theta should be less than equal to coefficient of static friction multiplied by mg cos theta. So ultimately we can see the condition for this is that tan theta should be less than equal to coefficient of static friction. So in other words, we say that if coefficient of static friction is greater than equal to tan theta, then the block will remain at rest when released. On the other hand, if mu s is less than tan theta, that basically means that mg sine theta will become larger than the maximum friction available. So in this case, what will happen? The block will slip. And if it slips, then the type of friction acting on it will be kinetic friction. So it will be mu k into n. In this particular case, it will have an acceleration down the inclined plane. Okay, so it will slip with acceleration e such that mg sine theta minus kinetic friction is equal to ma. So mg sine theta minus mu k into normal reaction is equal to ma. So that means mg sine theta minus coefficient of kinetic friction into mg cos theta will be equal to ma. So the acceleration will be given by this formula: g into sine theta minus coefficient of kinetic friction into cos theta. So these are the two possible scenarios, okay, or the two possible cases that can occur here. And how we can distinguish that which of the two cases is happening by comparing the value of coefficient of static friction with tan theta. If the coefficient of static friction is greater than equal to tan theta, then this is happening. It will remain at rest. There's no slipping. Okay. And if the coefficient of friction is less than tan theta, then it is this case. The block will slip. So this is an important sort of theorem or formula to remember, that how we can look at the coefficient of friction and compare with the angle of inclination theta to understand whether the block can remain at rest or it will start slipping when released. So for that we have to just compare the coefficient of static friction with the tan theta value. Okay, so make a note of this derivation please, and make sure you understand the free body diagram with resolution of forces and everything. Okay, so let's understand this with an example now. So suppose we have an inclined plane of inclination 37 degrees to the horizontal. So this is a rough inclined plane, and we have kept a block of mass m. So a block of mass m equal to 10 kilograms is placed on the rough inclined plane and released from rest. Calculate its acceleration, if any, and the magnitude of friction acting on it. If the coefficient of static friction is 0.8 and the coefficient of kinetic friction is 0.7. In the second case, the coefficient of static friction is 0.45 and the coefficient of kinetic friction is 0.4. Take g as 10 meters per second square. So take down the question. Now we'll see how we can do this directly. We know that formula, that tan theta formula. So here we know that if coefficient of static friction is greater than tan theta, greater than equal to tan theta, then the block will not slip. So its acceleration will be zero and a static friction of magnitude mg sine theta will act. Whereas on the other hand, if coefficient of static friction is less than tan theta, then the block will slip. And we know its acceleration will have a magnitude of because a kinetic friction of this much acts on it. Okay, so if you directly apply this theorem here, it's very easy. So you can see that theta equal to 37 degrees means the value we are after tan theta is 3 by 4 or 0.75. So that means that if coefficient of static friction is greater than equal to 0.75, then there is no slipping. And if coefficient of static friction is less than 0.75, then it will slip. So we already know that in this case, there will be no slipping. So acceleration will be zero. But in this case, there is slipping. So acceleration we need to find out. Okay, so let's find out this. So now if we look at the details in the first case, we can see that this component of weight mg cos theta, okay, that is going to be how much now? That is going to be 80 newtons. And this component of weight mg sin theta, that is going to be 60 newtons. So you can see the normal reaction we have is going to be equal to 80 newtons. Okay. So given that our coefficient of static friction is equal to 0.8, you can see that maximum static friction available to us is 160 newtons. Sorry, is 64 newtons. So we can see that mg sin theta is less than maximum friction. So you can see that acceleration will be 0 and there will be static friction acting over here. And that static friction will just balance. Okay. Therefore, static friction equal to mg sin theta or equal to 60 newtons acts on the block and its acceleration is 0. Okay, so remember you asked to also find out the magnitude of friction that is acting. So that becomes important. So that is this much here. Okay, mass of the block was 10 kg, theta was 37. So now same thing if we repeat in the second part, you can see that the only difference now is that the coefficient of static friction is a lot less. So coefficient of static friction being less, this part the coefficient of static friction was 0.45 and kinetic friction was 0.4. So we'll see that maximum friction available to us is 0.45 into 80, which is going to be a lot less. It is going to be 36 newtons only. So maximum static friction is less than mg sin theta. So therefore the block slips. And as it slips, there will be kinetic friction acting over here of mu k into normal reaction. It will have some acceleration E. So mg sin theta minus kinetic friction will be equal to ma, where the kinetic friction will be this much. It will be 0.4 into 80. It will be 32 newtons. So the amount of friction acting will be kinetic friction equal to 32 newtons. And substitute that here. So you'll get 60 minus 32 will be equal to 10a. So the acceleration of the block will become how much? 2.8 meters per second square. Okay. So that becomes the answer for the second part. So Tantri is very good. Your answers were correct. Kanishk, very good. Your answers were also correct. Only your values of friction, Kanishk, you need to check. Acceleration was correct in your answer. But in Kanishk, in the first part, it is given to you that coefficient of kinetic friction is 0.8, na beta? See, the question it is given to you, so you have to go with the data of the question, na? Coefficient of static friction was this much and kinetic friction was this much. The second part, the coefficient of kinetic friction was 0.4. So you cannot mix up the values, na? Okay, okay, fine. All right. So now one more thing. Sometimes in questions, if the coefficient of static friction is equal to the coefficient of kinetic friction, then only a single value mu will be given. In fact, in most questions, you will see that in the question only a single value of mu is given. So that means the coefficient of static friction is equal to the coefficient of kinetic friction, and is that value of mu. So the next few examples we will see that. Okay. So let's look at another inclined plane problem, but this time with multiple blocks. So we have this fixed inclined plane with a pulley around it. This kind of system of blocks. So this inclined plane is again at theta equal to 37 degrees. So both the blocks have same mass. Now a single coefficient of friction is given to us. Mu is equal to 0.2. It's a single coefficient of friction, and g is equal to 10 meters per second square. So find, and suppose the common mass of both the blocks is 2 kilograms. So find the acceleration and the tension in the string. So work this out quickly. Yeah, anybody got the answer yet for the acceleration? Okay, all of you are getting different answers. Let me check. So you should be getting this as the answer for acceleration. Tantresh, your answer is correct. Good. And then the tension you can see will become 19.6 newtons. Okay, so let's quickly understand the free body diagrams. So tension, weight here. Here we'll take the components of weight. Normal reaction, kinetic friction. Okay, so kinetic friction will have a magnitude of mu n in this case. So that is mu mg cos theta. Okay, because normal reaction will equal to mg cos theta. So now this has an acceleration a, this has a downward acceleration a. So we have mg minus t is equal to ma. That's for this block, let's say. And so this block is B. So for B we have t minus mg sine theta minus kinetic friction is equal to ma. Second equation. So you can add these two equations. And you can substitute this value here. Then put theta as 37 degrees. And then substitute this in equation 1. So you'll get the tension this will become your second answer. Sorry, 17.6. My mistake. Yes, that's correct. The tension will be 17.6. Okay, so hope this example is clear. So let's conclude with one final question. So now we have a situation like this. We have a block placed against a rough wall like this. And to keep it from falling, we are pressing it with a force like this, an external force into the wall. So this is a rough wall which has a coefficient of friction given to us as 0.25. Yeah, I'll just finish last question. So find the minimum magnitude of F external so that the block remains at rest. Given the mass of the block is 5 kilograms and G is equal to 10 meters per second square. What is the minimum amount of force that we require? Okay. This question should not take more than a couple of minutes. So let's finish up with this. So just start with the free body diagram. I'll explain. So you can see the moment we apply that force into the wall like this, the wall will apply an equal and opposite normal reaction. So the block and the wall are in contact with a normal contact force. So mg is trying to make the block slip down, but because there is a contact force, there will be friction. So now the only thing we have to make sure is that we can generate enough friction to prevent slipping. So you know the condition for that. So whatever force we apply, equal and opposite normal reaction the wall applies. So normal reaction equals to the external force. So the friction the wall is able to generate is such that maximum static friction is equal to mu n. That is mu into whatever force we are applying. So for equilibrium, the condition is that mg should be balanced by static friction. So that means mg should be less than equal to mu n. So that means mg should be less than equal to mu into external force. So this is the equation we need to solve. Yes, very good. Tantresh and Kanish, the answer is correct. So F should be greater than equal to mg by mu. So F should be greater than equal to 200 newtons. 200 meter, not 2 newtons. No? Divided by 0.25. It's 50 divided by 0.25. So it's 50 into 10 raised by 2 divided by 25. It's 200. Okay, so hope the question is clear, people. And with this, we conclude today's session. So please start working on questions from HCV, friction chapter. Questions 1 to 15. So please make sure you attempt these questions before the next lecture. And also anything pending from Newton's laws before completed. You can also start doing questions from your module exercises and start going through the solved examples in the module, the illustrated examples. So that's it for today's class, people. Wish you all the best.